Welcome back. Let's do a Wheatstone bridge problem. Okay, so a Wheatstone bridge is a device used for measuring resistors, right? So you're given a balanced Wheatstone bridge. So you're given this guy. They've got a 6-volt ideal voltage source, and then there's a bridge, a Wheatstone bridge, this one. So there's 3 resistors in here, R1, R2, R3, that are known. And one of these is a variable resistor. Usually it's R3, but they're all given. So this one's 200 ohms. This one's 500 ohms. This one is 800 ohms. Okay, and this one R sub X is unknown. So you're given a balanced Wheatstone bridge, which means that in here they put a Darson-Ball movement and adjusted it such that it says 0 amps. And that there's no current flow in here. So I'm drawing it with a dotted line because if there's 0 amps flowing across this, that can only happen when the voltage potential is 0. So the voltage across here is 0, and the current through here is 0. So basically this movement is having no effect on the circuit. There's no current through it, there's no voltage across it, it's like it's not even there. So you adjust it such that its effect disappears. You adjust it such that the current through it is 0 and the voltage across it is 0. And then you could take it out of the circuit. And at that point, that's what we mean by balanced. At that point, this formula applies. The unknown resistance is given by this formula right here. And that's what we're asked to find. We're asked to find a couple of things. We're asked to find R sub X for this balance condition, and then P in all resistors. What is the power in each one of these 4 resistors? And then find P max and P min. Okay, the resistor with the largest power draw and the resistor with the smallest power draw. Okay, so solution you could write. So R sub X is just going to be this formula. It's going to be R2 over R1 times R3 over 500 over 200 times 800. It's going to be 2000. Right? That's the first one. Just a simple application of a Wheatstone bridge formula for the balanced condition. Right, very easy. Then let's see. We want to do the power. So we have a couple of power formulas. We have P equals IV. We have P equals I squared R. We have P equals V squared over R. We've got these 3. You could do some kind of voltage division, figure out what the voltage is across these. You could do that, or you could figure out what the current is. Let's use the current approach. So let's call, where should I write? Let's call this I sub A, and let's call the current through this branch I sub B, and let's call this guy the I sub S for the source. Okay, so we can use Ohm's law. So V equals IR. So here we have 6 volts. Let's call this terminals A and B. So there's 6 volts across AB, right? There's 6 volts from A to B. So there's 6 volts across this branch, and there's 6 volts across this branch, because they're both, both of these branches are between A and B. Or you could say, this branch is in parallel with this branch. So parallel branches have the same voltage. There's different ways to say the same thing. And that's kind of what we're trying to do in this chapter 2 and chapter 1, is just get basic familiarity with some real simple circuit behavior is kind of what we're doing. Anyway, so the voltage across this branch is 6 volts, so we can find IA. So IA is going to be, you solve Ohm's law for I, it's going to be V over R, and where V is the total, is 6 over 200 plus 800. It's going to be 6 milliamps. Likewise, I sub B has the same 6 voltage, 6 volts across it with these two different resistors, so it's going to be 6 over 500 plus 2000. It's going to be 2.4 milliamps. Okay, so we have the current through this branch is 6 milliamps, the current through this branch 2.4 amps. We can use this this formula right here. We can use that twice. So the powers that be, the powers are, so the power in the 200 is the current in the 200 squared times 200. So it's 7.2 milliwatts is what that works out to be. And the power in the 800 is the 6 amps, you know, through the 6 milliamps. This is milli, and this is ohms. So the answer is milli. And if you're, be careful. Oh yeah, this is it's a much bigger number, but it then moved over. It's milli. The answer is not milli per, just because this is milli, but just I'm saying be careful with the units. This is 6 milliamps, or 6 times 10 to the minus 3 amps square, which gives you a big number. Then times 200 is pretty big, but then you know, it ends up working out at 6 milliwatts. You know, so be careful with that. All I'm saying is put in the full, you know, 6 times 10 to the minus 3, you know, in your calculator, because you're squaring this, and it's easy to mess it up when you're squaring things, when you're squaring, you know, milli and micro and mega and stuff. So be careful. Anyway, the second one is this thing, and it ends up being 28.8 milliwatts. And, you know, pretty straightforward, the rest of these guys. 500 is going to be, so you've got 2.4 milliamps running through the 500 and the 2K one. So this can be 2.4 squared times 500 is going to be 2.88 milliwatts. And the power in the 2K guy is going to be 2.4, right? It's got the same 2.4 amps running through that branch times 2000. It's going to be 11.52 milliwatts. Okay, this one's the big most. This guy, this is the most. And this is the least. All right. Pretty straightforward Wheatstone bridge problem. All right, bye.